Okay, very good afternoon. Audible? This is audible now. So, today's class, we will move on with Lipschitz continuity, Lipschitz smoothness, and so on, and move on to algorithms for optimization. That's our last building block for algorithms. So, recall that we concluded our analysis of necessary and sufficient conditions, largely sufficient conditions. We'll do more of necessary conditions as we progress. And we left off at this point of the formal optimization problem. I've put this convexity as a rider, and as I said, convexity will always emerge as sub problems, right? So for the time being, forgive the use of the word convexity. It's not necessarily meant to be imposed everywhere. So we have an objective fx that we want to minimize, desirably convex, subject to constraints that should also be convex. So min over fx such that the domain is convex. And the way we characterize a convex domain is a bunch of inequalities gix less than or equal to 0, I equals 1 to m such inequalities, each gi is convex, and at jx the inequality should be 0 for j equals 1 to n. Okay, and the fact that g's are desirable to be convex emerges from the fact that if the function is convex, its sub-level sets are also convex, right? G1, right, equals 1, G1 equals 3, and so on. So sub-level sets are also supposed to be convex. Okay. So these are special cases. Now, the GIX less than or equal to 0 for I equals 1 to m is basically intersection of multiple convex sets. And we have seen again that intersection is also convex. In fact, it also is closely related to the dual characterization of convex sets as an intersection of multiple half spaces. Remember, a primal way of describing a polyhedron is through a convex hull of points, and a dual is description as intersection of half spaces. So, I mean, good to keep looking at multiple perspectives. Of course, both m and p both could be 0. That means we may have no constraints at all. And so far, what we have seen, right? How do you minimize such a function? Well, if x is in the interior of its constraints, is within the set, then 0 being in the subdifferential of f is a sufficient condition. Okay, so let's also now stitch together the story. The story is, or for solution, if x is in the interior, let's just call this the entire domain, right? Entire thing is the domain. If it's in the interior of domain of f, then 0 being in the subdifferential of f is a sufficient condition. I just put an X star condition for optimal solution at X star. Um, Now the other perspective is, what if these constraints are characterized with respect to discrete functions? What if the function, if it's a function if itself is discrete? Okay, and that typically happens. For example, I gave you the image segmentation problem, or I'm trying. What is image segmentation? I want to know which pixels should correspond to the car or that bench in this class, and which pixels should correspond to the walls. Right now, relaxations are basically when you take the function f and a discrete function f and relax it to be a convex, may not be convex, as a continuous function, may be convex, may not be convex. So these relaxations may not be convex everywhere, though it might be convex in some regions. So I was trying to show this example. You remember the part of speech tagging. If at every word you may have multiple parts of speech, and you're trying to find the configurations of parts of speech that have the highest level of energy, right? Okay. So, but this is the overarching problem. Um, Now let's move on to understanding what could be the necessary conditions, right? This is just one sufficient condition. Sufficient condition saying like, if this happens, then I have a solution. Necessary condition. What do you know about necessity if X star is in the interior? If X star is the interior of the domain of F, what would you guess? What's the necessary condition? Well, if the function is differentiable, we haven't, right? If the if F is convex, then I know that the subgradient exists, right? So if it's convex, necessity at F for differentiable X. So this, I'm not even insisting that. I'm getting a call from the director of. By the way, the good news is that Bharat thanks to all kinds of pushes from the top, becoming a national initiative. That we just keeping us super busy. Um, so yeah, thanks. So necessity at X star for a differentiable function X, it, will be what? If it's differentiable, no convexity at all, then the gradient f at X star must go to 0. So it's not even insisting on convexity. Question is, what if X is not in the interior? What if X lands up having one of the GIX to be equal to 0? What do I do? Okay, this is intuition. We are not going to prove anything right now. We need more ammunition. So here, right, if you have constraint optimization, and if you have a case like this, right, so um, the point of optimality is lying in somewhere in the boundary, like in this case. What could you guess, right? Now, it turns out that a point X star is minimizer if and only if. Okay, so this, now we're going a little overboard and saying if and only if, which means there's a necessity and sufficient. We already talked about sufficiency if F is convex. You're saying if it's convex and if it's differentiable, then a sufficient and necessary condition is that the gradient makes an acute angle with respect to x minus x star. Okay. So what does this mean? So this means I'm trying the constraint case. So let's just say this is x star, and the gradient of f at x star, and this is some other point x. Okay, so x minus x star should make it was f at x star. F minus sorry, gradient of f should make an acute angle with x minus x star. I'm deliberately illustrating this in the case of the boundary point, right? This is, of course, this is a sufficient condition. So I won't talk about sufficiency here, right? Sufficiency, we'll figure. I mean, you can see that if gradient vanishes, obviously it's sufficient. But even if it doesn't vanish on the neighborhood, on the boundary, it is a sufficient condition. But I think what is interesting is necessity for now. If f is convex, that this makes an acute angle. Intuitively, what this is saying, that if you're trying to make or reduce the value of the function along any direction, then you'll have to violate the constraint. You see what's happening. If I have to reduce the value of the function at x star, then I have to go against the gradient, isn't it? If I have to reduce the function value f here, I'll have to go somewhere against the gradient. Moment I go against the gradient, I'm going outside the domain. This is the domain in the sense the, the constrained region. Is this clear? So this looks appealing as a necessary condition. In fact, sufficiency is very easy to prove. But I hope this is making sense. Necessity of under constrained conditions. In fact, I'll say sufficiency and necessity is that this gradient makes an acute angle with respect to okay. Yeah. Here it's not open, right? You mean the previous condition? If say differentiability, you can always only talk in terms of open domain. See, the moment you start with the boundary, then you have to talk about left and right. Now, that is by design. But here, I mean, we are going beyond the interior. The domain is open. I mean, the differentiability is insisted on open domain. That's all. But we are still coming up with a condition on a boundary point. This includes a boundary point. And we are not saying that the function is not differentiable on the boundary point. Okay. So I have also tried depicting it further here. Like if you had a function of this sort, if it looks convex, then all we are saying is if you are at see, the function could have been non-convex in this region, right? So it's kind of becoming non-convex here. But I think all that we are trying to say is the condition matters here. That the gradient of the function, obviously the gradient will be lying in just one dimension here. So I can't depict it easily here. But the gradient should make an acute angle with respect to x minus x star, as even if x is here. Okay, so there are two cases. One is x in the interior, which means sub-differential, zero sub-differential, or gradient vanishing is sufficient condition. But I think our entire focus today, our entire focus in this slide is a case 2, which x star is in the boundary. Is all clear now? So the generalization of this, of course, will require us to know, characterize the boundary. This is just intuitive enough, but I can't use this procedurally. I'll have to write down the gradients of G as well. because I'll have to characterize the boundary and conditions thereof in terms of GIs. But for now, it is good enough because right now our motivation is to get into algorithms. We'll revisit constraints if there is time. We'll have to get to post midsem. We'll be focusing on seminars and projects largely, but we'll see if we find time. We'll squeeze in a bit more of analysis here. So here are examples of programs, linear and quadratic, where the function, in the case of linear programs, is a linear function. The constraints are also linear. Inequality, linear inequality. Quadratic programs, on the other hand, you have a quadratic function, and again the constraint is linear inequality. So when is this quadratic program a convex optimization problem? Going by our definition, yes. When would you say that this quadratic program is a convex optimization problem? So far, we did not even specify that the function is, or rather the optimization problem needs to be convex. We haven't said anything about the nature of the A's and the Q's. But if I wanted this to be a quadratic optimization, or a convex optimization problem, what would I require of Q and P? Actually, there's only Q and A. Q and A. Yes. It's a necessary condition. I'm saying only if. Anything about Q? Anything about A? Positive, positive, positive semi-definite, right? If Q is positive semi-definite, you don't need anything on A. A seems fine because the linear inequalities, convexity is always going to be kind of guaranteed, right? So quadratic expressions that you need to take more care. You've done this before. Okay, I think with that, some preliminarily we have completed the constrained convex optimization problem and optimality condition. More later on, I think you have good enough intuition. What we'll do is now to really move towards algorithms, we need one more tool, just Lipschitz continuity, Lipschitz smoothness. These tools will be helpful in analyzing convergence, and you'll literally not find any proofs around which don't make use of these conditions. So it's important for us to go through that. And then we look at gradient descent analysis and Nestrov's accelerated gradient descent. All of that will be a follow-up, not more, right? Now on Lipschitz algebra, what is Lipschitz about, right? Convexity was all about curvature, and strong convexity was about, of course, curved up, but strong convexity said you must at least be so much curved. Lipschitz, on the other hand, is putting some kind of an upper bound on the rate of change of the function or rate of change of its derivative. That's the basic idea. So let's write on the broad idea, then we'll go into some details and examples. And of course, we'll do what we like to do, come back to our canonical ML problems. So it's a kind of upper bound rate of change either of the function or of the gradient. And why would you be interested? So when we look at convergence of all algorithms, right? Let's say we do gradient descent. You want to make sure that the steps are the steps that you choose for the gradient descent are good enough that the function converges to the optimal point, but you also want to make sure that the function doesn't overshoot, right? So when you put an upper bound on the rate of change of the function, you're kind of assuring yourself that you won't overshoot, right? So that is the goal. to guard against algos overshooting the point of optimality. Okay. But yeah, there are some links keep evolving all the time, so you will come across a lot more. So what is Lipschitz continuity? Lipschitz continuity has to do with the function itself. A function f is Lipschitz continuous with a constant L. So if the rate of change of f is upper bound, f of x minus f of y, absolute value is less than equal to L times the distance of x from y. And we look at Euclidean distance. Now, are you tempted to do something based on this condition? See, for convexity, we never stopped at the basic definition. What did we do? We looked at first order conditions. We looked at second order conditions, right? So these are curiosity questions for you. Can I similarly extrapolate all of these to first order and second order conditions? Okay, so I'll look at gradient later on. So what is your intuition? Intuitions are very important here. What is your intuition? Would this extrapolation hold actually? What would be that extrapolation?
So the it will be less.
So the intuition says that you would have the norm of the gradient, right? Less than equal to L. That's if it's differentiable. Does f have to be differentiable here? Does the condition or definition insist on differentiability? No, right? So the rate of change, you can go from this ratio to its gradient only if it's differentiable. But otherwise, that you're right. So all we are saying is the function is not changing too fast or too soon, and then a linearly scaled upper bound on the absolute value of the difference, which corresponds to the upper bound on the gradient norm if the gradient exists. Okay. Of course, when we say Lipschitz constant LV and x and y, L is constant. Are x and y fixed? So what do I have to talk about f and x and y? What should they be fixed points for any pair of points? Any pair of points. Here it is for all x comma y in the domain. However, here when we look at the first order condition, we're looking at for all x alone, right? Just be a little careful, you know. Sometimes these are where the intuitions can be challenged. Suddenly, the for all quantifier, which was on 2 x and y, has now become a quantifier only on 1, and there could be a slip somewhere. Okay, but otherwise, yeah, this looks correct. And yeah, besides quantifying, limiting, right? Limit on the rate of change of the function. What you also need to look at is, you know, when you say every pair of points x and y, we played safe in the past. We always looked at direction, right? So instead of saying all x, all y, you can say, well, under any direction v that you move from x plus hv minus f of x divided by h. That can be characterized as a directional derivative. So instead of just jumping from for all x y to for all x, it'd be safe to say, well, for all x comma h, h is a direction, we should have this. Sorry, v, I mean v, the direction v. Okay. So dv fx absolute value is less than equal to L. That's a safer route. Okay. Any questions so far? But then, yes, we can make that jump. Now the other thing is, okay, all this is fine if the function is differentiable, but what if the function is not differentiable but convex? For a convex function, what do you know? There always subgradients exist, right? So I mean, this extrapolation to first order, this is if f is differentiable, but you also have another condition, if f is, so we will not bring up convexity needlessly, okay? Will be on a need to basis. But if it's convex, then I know that that the subgradient is a non-empty. Right, for all x, subgradient is non-empty. So question then is, okay, I'll put this in a different color. So question, can I say the same thing about all subgradients, which is at x, which is all h in the subdifferential of f at x? By definition of subgradient. Sorry? So it's a good point, right? But you're not looking at the rate of change of the function being approximated as a gradient. But what you're looking at is the convexity definition, right? F of y is greater than or equal to f of x plus subgradient transpose x y minus x. I won't take the trouble of writing it all over, but you can imagine. If I have f of y minus f of x coming on one side. Okay, so this should be also fine. So this should be a broader definition. Okay, so then the question is yes. Answer is yes. So again, you see, no, we are not imposing convexity, but convexity is so beautiful. Convex regions give you this entire access to subgradients. Okay. So now we have gone, we said earlier it was only in terms of the gradient, but now we are looking at subgradients as well. Okay, so now let's look at some calculus properties. Okay. What do you think about the sum of two functions? What about the rate of change, upper bound on the rate of change of sum of two functions? Let's say function f1 has Lipschitz constant, continuity constant L1. So f1 has Lipschitz constant L1 and the second has L2. What do you think will happen? The rate of change of f1 plus f2, would you upper bound it? And how would you upper bound it? So his point is if a differentiable, I could actually just upper bound the respective gradients, the norms of the gradients, and then use triangle inequality. You will need triangle inequality, even if it's not differentiable. Actually, it will be the same triangle inequality. I mean, why wait for a different derivative, right? So f1 plus f2 is is going to be will be L1 plus L2 so this is fairly straightforward. Sums. In general, sums of functions have the same properties as original functions. Right? So you basically use this norm of a minus b less than or equal to norm of a minus c plus norm of c minus b. In this case, it will be the respective function differences. Um, okay, so this is done. F1 plus F2 is L1 plus L2 Lipschitz continuous. What else? Compositions. Can you say something? Compositions. F of G. Or how about composition? Rate of change of a function composed with another function which has a particular rate of change. Product. But why are we jumping away from composition? All the cases that we considered earlier. So composition, is it tricky? Does it generalize? See, the tricky part here is we're looking at rate of change. Differences at two different points. See, this is exactly the challenge. Right? This is for all x, y. Right? In convexity, we said, well, convexity also originally we started with x, y, all pairs x, y. But there was still a difference, right? There we were still pivoting on some x. Right? I mean, for example, the first order property we said gradient at x. Here it's for all pairs. I'm telling you that is creating a little bit of challenge. It's not as ubiquitous. Well, the other advantage is it's not insisting on convexity. So I mean, both have their interesting spaces. So product seems to be a more natural thing to look at. Compositions are not. I mean, there's no generic statement I know of compositions. So let's consider product. Somebody suggested product. So what happens F1 times F2? So if F1 is Lipschitz continuous with L, F2 with L, then what happens to F1 plus F1 into F2? Going by the same thing, right? So I have I'll have F1 F2x minus F1 F2y. Can I say that's less than or equal to F1x minus F1y into F1 F2x minus F2y? Like I had triangle inequality, can I just extrapolate using products? So it turns out that it's not that straightforward. And why is it not straightforward? So if I write this F1 F2 x minus F1 y, I mean it's a composition. I mean a composition, but in a product composition. So maybe you should put an x here and an x here. That composition, right? Maybe it's dangerous to not write this. So let's write this F1 y. So when do you think this can be written as less than equal to? So I need some inequality with respect to F1x minus F1y times F2x minus f2y. So take all those cross product terms, right? f1x, f1 f2x, f1 f2y, f1 f1x f2y, f2x f1y. Those cross terms are a problem. So how can I get rid of those cross terms? So I need to get to this point, right? If they are monotonic, you mean monotone? Then I mean the only monotone definition we saw was with respect to gradients and subgradients. I mean this is vector valued. Now x and y are not comparable necessarily, right? Otherwise,
Okay.
so x and y may be scalars, in which case you can talk of monotone. But if x and y as vectors, what do you do? So can we do the following? Can we kind of assume that um, the f1 and f2s are bounded? So if they are bounded, I can take these cross product terms f1x, f2y, f1y, f2x, or whatever, and I can assume that it will never exceed certain value, right? Because all the others are positive. f1x, f1x, f1y, and f2x. Sorry, yeah, f1x, f2x, and f1y, f2y. You take the product, they are positive. The issue is the cross terms, they're negative, right? But if I assume that the functions are bounded, the inequality could actually be preserved. Why? Because I'll say, well, this is less than equal to f1x, f2x minus f1y, f2y. I'm just applying here, is less than equal to this product, which will amount to L1 times L2. And there's a negative term. So I'm this absolute value, I'm kind of dissolving for now. You have to consider cases. What if the f1 minus f2 is greater than 0? What if it's less than 0? So I'm assuming all that hard work you'll do. Hereafter, we'll avoid doing too much hard work. Only do intuition. We'll otherwise have no time, right? But the idea is those cross terms, if we can somehow bound them, then we can sail through. Okay, so product of bounded L1 and L2 Lipschitz continuous functions. Okay, so what are we saying basically? If fx gx minus fy gy is less than equal to some bound of fx minus fy into gx minus gy. Bounded means the function absolute value will not exceed certain threshold. So you need to work this out. Do it as homework. Okay, so product of two Lipschitz continuous and bounded function is also Lipschitz continuous. Now we look at the next property. I'm going to erase the right hand side, which is smoothness. So smoothness has to do with the rate of change of the function's gradient. So we'll have analogous journey here. So basically saying function f is smooth if its gradient is Lipschitz continuous. So now instead of thinking about a function from Rn to R, think of a function from Rn to Rn. Okay, that's the difference. The only difference is f. Now we are talking about f, which goes from Rn to Rn, right? On the left hand side, the whole description was on f, which goes from Rn to R. So let's try and extrapolate. We're dealing with a vector. So the notion of smoothness, right? Okay, so Lipschitz continuous. It's continuous. And here you have Lipschitz smoothness. I'm going to apply the same stuff. Instead of absolute value of the functional difference, I'm talking about the norm of the difference of the two functions. So that's just applying the definition, right? And what does this amount to? So now we are getting into some more interesting territory, and I'll tell you, Lipschitz smoothness is more interesting than continuity. Why? Because now by going to the first order, well, I never talked about second order on the left hand side, but here on the right hand side, we can potentially go to second order. That's one thing. And because of that, we are now talking of curvatures, right? Rate of change is fine, but rate of change of the gradient of the function being upper bound is amounting to saying that the curvature is upper bounded. Okay, so this is an interpretation here. So basically, it's like saying that the function has an upper bounded curvature, the blue one here, right? So when we talked of strong convexity, we had this pink one, or orange one. We are saying that, remember, yeah, there was this lambda or whatever, right? What we use there, C, right? We use a C, but I've written lambda on the board. So basically, we are saying V transpose Hessian V should be greater than or equal to lambda. That means the curvature is at least lambda in every direction. So this is a lambda part. Here we are saying that the rate of change, now we'll extrapolate this to curvature, is saying that this L is basically an upper bound. You take any V direction, V transpose Hessian V is sorry, is less than equal to L. Okay. So therefore, many convergence algorithms become the best convergence is when you have both Lipschitz smoothness and strong convexity. This is strong convexity. And the one and two is the Lipschitz smoothness. And we just call it L smoothness. Right. So the gradient of f being Lipschitz continuous implies this upper bound, and it also implies that the Hessian has an upper bounded eigenvalue. I mean, it's like basically saying all the eigenvalues of Hessian should be upper bounded by L. The eigenvalues are the curvature along the canonical, the cardinal directions, right? Actually, cardinal in the sense is eigenvector directions. Lambda 1 corresponds to eigenvector V1 direction, and so on. But here we are saying, well, no matter which eigenvalue you take and which direction you take, the curvature is going to be upper bounded by L in all directions. Okay, so I have one question. So we have really jumped. I'm going to give you an interesting exercise in the class. Okay, I need to fill up this square box. So what is the idea? Well, I've already given you a hint that, and you can prove it also, that the Hessian will have an upper bounded eigenvalue, which basically this is a positive the counterpart of positive, strongly positive definiteness, right? You're putting an upper bound. And that corresponds to, as I said, the blue curve where there is an upper bound of the curvature. And strong convexity is a lower bound of the curvature, which is the red part. Now, I want to recall that in strong convexity, there was one more equivalent condition, which is a quadratic lower bound. You remember this condition? F of y was greater than or equal to f of x plus gradient of f, gradient transpose y minus x, which is a lower bound. But we said, well, there's a not just a linear lower bound, there's a quadratic lower bound, and I put m by 2 y minus x norm square, right? Can you think of an equivalent quadratic upper bound condition here? What would that be? Because we have literally jumped with a leap of faith. So can you suggest what this expression might look like? Do you think it will just look like the same thing? L by and what will happen to the inequality here? Will the inequality remain the same? F of y is greater than or equal to f of x. The quadratic curve will become upper bound. So then what will happen to this inequality? So here it is, remember f of y was greater than or equal to. The point lies above. Earlier it was just the gradient approximation. Now it is a gradient approximation, quadratic approximation around the gradient. But that is going to be a lower bound, the upper bound. F of y less than or equal to f of x plus this dot product. And as we are pointing out, this m will get replaced by L. So m by 2. So this is my equivalent Lipschitz smoothness condition. And now you start seeing the tussle, right? Convexity was getting a very free ride. It said, oh, well, f of y is lower bounded by linear approximation, quadratic approximation. Now, if in addition to convexity, right, which said, right, let's assume, right, I'm going to put this in a corner here. So interesting tussle with convexity. And it doesn't really contradict convexity, by the way. So, right, if I had only convexity, not even strong convexity, let's say, just convexity and Lipschitz smoothness, I would say f of y is greater than or equal to f of x plus this dot product of gradient with y minus x. I'm saying the function has this lower bound thing. May not be even a quadratic curve, maybe just a hyperplane. So if I had this green along with the blue one, even if I didn't have the orange one, which is strong convexity, even then I have something interesting to offer, right? Because I'm not letting the convexity get a free ride by lower bound. I'm putting an upper bound as well. Okay, so we'll see all these combinations. Combinations will be convexity plus Lipschitz smoothness, strong convexity plus Lipschitz smoothness. We'll also have, of course, convexity, which are weaker ones, plus Lipschitz continuity. LC is Lipschitz continuity. Okay, LS is Lipschitz smoothness. LC is Lipschitz continuity. You can use these, or just sometimes you may use C and S. C and S. So convexity plus Lipschitz continuity also can be considered. In fact, strong convexity plus Lipschitz continuity can also be considered. Can you put an intuitive ordering? Which of them is the most desirable for convergence? Yeah, we have not even talked about convergence and algorithms. But this is how you should think. You should think a little ahead, right? Because that's you need to motivate ideas and not just keep defining and then do this boring job of revealing the obvious, right? So what do you think will be the ordering? Which of them will give the best speed up? Okay. So what do you say? Strong convexity plus Lipschitz smoothness. Okay, so this is the highest marks. Second, what do you think will be the second best? Convexity plus Lipschitz smoothness. You feel this is very powerful. Okay. And then third, okay, so then you think strong convexity plus Lipschitz continuity? Yeah, some people have given up. So it doesn't really matter. Once you're out of strong for Lipschitz smoothness, all of them are equally good or equally bad. We'll see more of that later, right? So, okay, so this now it's interesting. I mean, this is you're correct. This description was correct. It's interesting that in this entire process, new algorithms get discovered. Okay, I'll repeat this point again. In fact, people have not just looked at these combinations. Researchers also looked at upper bounding. How fast can an algorithm work when you have convexity or so strong convexity plus Lipschitz smoothness? And I must tell you, gaps were discovered in point two between what is possible, I mean, the worst case, through some pathological function, and what was actually being done then. And then people thought, oh, there is a gap. Can there be an algorithm that can fill up the gap? And that has led to this entire accelerated gradient descent. All that we enjoy today is because of someone studying a gap. So please understand, analysis is very powerful. Analysis gives you, opens up doors. It's not just a dry exercise, convexity in the yesteryears, and therefore we have nothing better to teach. No, it is still relevant. Maybe I don't have better things to teach, but it's still relevant. The point is, uh, analysis gives you this big gap. Okay, I think we have motivated Lipschitz continuity and smoothness well. Let's take examples. I'll take lots of examples, culminating in our favorite ML examples. Okay. Okay. By the way, an important point is M and L. What should be the relation? L and M. Oh, sorry, not M. M was this upper bound. So this actually, I'll replace this with lambda. M. This is lambda. So what should be the relation between M and L? Yes. M should be less than equal to L, right? The lower bound should be less than equal to upper bound. Okay. So let's take some examples. X square. X square is the most obvious example of a function that would be both strongly convex and Lipschitz smooth. Why? Because if you take the double derivative, it is 2 is upper bounded by 3 and lower bounded by 1. Some constant. It's so very simple, right? So a Hessian is 2, which is upper bounded and lower bounded very obviously by 1 and by 3 and 1. Lipschitz smoothness and strong convexity. Okay. You can also analyze this using, as I said, the definition itself. You can also write it this way, right? I mean, instead of jumping to Hessian, you can say, well, 2y minus x is less than equal to L of y minus x. L can be basically 3 or whatever. So how about x raised to 4? So x square is very easy. So Lipschitz smoothness example, our favorite example is L square. X square. What about x raised to 4? Does there exist an L such that x square minus y square is less than or equal to L times x minus y? Does it? X square minus y square is x plus y into x minus y, right? So there's an upper bound on x minus y. But what about x plus y? Is x plus y upper bounded? You understand what I'm asking? The Hessian is x square. Actually, I'm sorry, I've considered x cube by 3. X raised to 4 will come later. I'm sorry, I've jumped already. I've looked at x cube by 3. So for that, Hessian is x square. Not Hessian, gradient is x square. And for that, you will consider x square minus y square. So I'm considering x cube by 3. I'll actually erase Lipschitz continuity. There's not so much, at least the calculus part I'll erase. X cube by 3. It's correct. X square minus y square. Absolute value is less than or equal to x plus y into x. Absolute value of x minus y. What about this? So I know that, let's say, x minus y can be upper bounded, yes or no? It depends on the domain. But this x minus y doesn't matter because it can stick around in the Lipschitz smoothness case, right? So I don't care for x minus y because I all I wanted is L times x minus y. So x plus y is that bounded? No, right? So that is the problem. The problem is not x minus y. The problem is x plus y. So is there an L such that x square minus y square is less than or equal to L times x minus y? And the answer is right. If you ensure that x absolute value of x is less than or equal to alpha, then you could, if for a bounded interval, a bounded set, right? Then you could consider Lipschitz smoothness of x cube by 3. It's not otherwise. Okay. So this is fine. This is fine for uh, x cube by 3. X. This requires x plus y is less than or equal to L. Some L. Then you can talk about L as a Lipschitz smoothness. What about x raised to 4? We need to do x raised to 4, right? X cube is fine. What about x raised to 4? So Hessian of fx is 12x square. So can I say this is upper bounded? Not on absolute terms, right? I need this to be again fx is bounded by some theta, right? So point is functions of, I mean, generally you need to bound them, and only functions that are symptotically growing quadratically, only those can be smooth, Lipschitz smooth everywhere. Otherwise, you'll have to consider some bounded range. So I think this gives you enough exposure to, or an intuition of when you can expect, right? So X raised to 4, you please study this. Right? I mean, I've given already the answer in some sense. Why is it that it's not Lipschitz smooth? Is X raised to 4 strongly convex, by the way? Is X raised to 4 strongly convex? So the Hessian 12x square is greater than or equal to, is it greater than or equal to some constant always? Huh? 0. 0. 0 certainly, then that's only talking about its convexity, right? But is it strongly convex everywhere? Not globally, right? All you can say is 12x square is greater than or equal to some very, very small epsilon for all x greater than or equal to square root epsilon by 12, something like this. So basically, even if you consider a small enough epsilon and x to be outside that, it's still strongly convex for most parts. Right? But so this is not strongly convex. It's convex, but 12x square is still better will behave from strong convexity perspective. But we have a major challenge with respect to x raised to 4 when it comes to Lipschitz smoothness. Okay, so I hope that uh, asymmetry is somewhat clear here. Some more weird examples. Okay, I'm taking f dash x as absolute value of x, or you can think of f dash x as a new function. Doesn't really matter. Let's say f dash x is a new function. Um, Later on, you can consider f dash x to be the derivative of x, some weird function which gives you derivative as absolute value of x. So what about that? We'll go a little faster. I brought up absolute value because a lot of the characterization we have seen on the slides today is all about absolute values, right? Continuity, smoothness, etc. Anyone? So basically, it's akin to asking the difference at 2 points is less than or equal to x minus y times L. And is there some L? So if you consider the substitute for x here and absolute value x and absolute value y, obviously it is less than or equal to x minus y times L, right? But triangle inequality, right? So f is smooth. Now if f, basically if you have to consider f to be the function, then f is smooth. Or I could just say comma f dash is Lipschitz continuous. And f dash is Lipschitz continuous. Okay, but then of course the other challenge is f double dash doesn't even exist everywhere. So it's differentiable almost everywhere. So this point of differentiability almost everywhere I'm going to bring up next. Right? So many of these functions you'll find that they are well behaved in terms of derivatives pretty much everywhere. Just that some places they're not differentiable. So f dash, so if the function is the absolute value of x, absolute value of x is not differentiable at 0, but it's differentiable everywhere else pretty much, right? That's what we call as, or refer to as differentiable almost everywhere, right? Formally, you say it's differentiable almost everywhere if the set on which it's not differentiable has measure 0. So in this case, it's just 1.0. So it's non-trivial. So it's a trivial amount of elements where it is not differentiable. Okay, so so f dash is not differentiable everywhere, but it's differentiable almost everywhere. In fact, a function that we have seen, our favorite function, 1 norm of x, is also differentiable almost everywhere, except for a configuration which has, let's say, one of the components to be 0. Okay, so more questions. Is every subquadratic function Lipschitz smooth? So if you say take x fx to be absolute value of x raised to 3 by 2, so it's subquadratic. So we say quadratic is very interesting, right? Quadratic rate of growth. But what if it's subquadratic? Right? And let's say we are considering a closed set, so that 0 is element of that set. Is this function smooth? Yes. The gradient of f dash. Okay, think of f dash for now as a new function, a different function. But as an intermediate step, I also consider f dash to be the derivative of f. Okay? So I'm just using taking flexibility in considering f dash as a primary function versus f as a primary function. So here I'm considering f dash to be the primary function, and f so far, sorry, before this, but here I'm considering f to be the primary function, x absolute value of x raised to 3 by 2. So the gradient f dash vanishes. Also, gradient f dash is infinity at x equals 0. I mean, rather doesn't exist. But it is still, um, differentiable almost everywhere, right? So is it Lipschitz smooth? Absolute value of x raised to 3 by 2. Can I actually write down any of these conditions? In fact, double derivative also you can consider. Okay, so if let's say at x greater than 0. So the way you should handle this is, okay, let's consider different intervals. Never get scared, right, by seeing a function which is not differentiable everywhere. Write down the conditions. If x is greater than 0, it is 3 by 2 raised to x, 3 by 2 into x raised to half. If and in that case, double derivative is 3 by 4 raised to x square, I mean, square root of 1 upon x, right? So this function, if you like, right, since you look at this form, right, it is not globally smooth. Right? You can't say this is upper bounded by some L. Can you? This function is an upper bounded by some L? No, right? X can get infinitesimally small, in which case square root of 1 upon x can get very large, right? So this is not globally smooth. So subquadratic functions, again, just because x raised to 4 is not smooth, doesn't mean that subquadratic functions become smooth. But many subquadratic functions are smooth. If you remove the absolute value, x raised to 3 by 2, do you think it's smooth? Instead of absolute value of x raised to 3 by 2, just x raised to 3 by 2, do you think it's smooth? Sorry? X raised to 3 by 2 looks smooth, right? The problem is absolute value here. Otherwise, x raised to 3 by 2. We can actually write down examples. X raised to 3 by 2. So some quadratic function. Lots of subquadratic functions are smooth, but there are these exceptions, pathological cases of this form which are not. But even this is smooth in a bounded and closed interval not containing 0. The problem is 0. Okay. Now I'll come up with a very interesting statement which only we'll look at it intuitively. We may not be able to, certainly not prove, but we may try and map examples we have considered so far. Okay? So what's the statement? We already talked about differentiable almost everywhere, right? And we are saying it's continuously differentiable, which is continuous, and derivative is also continuous, almost everywhere. This is continuous. This is just continuous. But if f is continuously differentiable almost everywhere, it is also Lipschitz continuous. This is a claim. Okay. It's even in with convexity we talked about only pathological cases, right? So the pathological case here is when it is um, is where it's not differentiable and infinite number of points or uncountable. Infinite is possible, but uncountable number of points. Only then we have a problem with Lipschitz continuity. But otherwise, if it's continuously differentiable almost everywhere, then it is also Lipschitz continuous. Actually, the point is about measure the set of points where you're going to look at whether derivative doesn't exist. That should be very trivial. I mean, should be a very, very small set, right? So, yeah. So it's, but roughly speaking, what you're saying is correct. Right? We should actually look at measure theory to exactly characterize this, but you're right. Otherwise, so this is a big statement. Right? Lipschitz continuity seems to be otherwise on the offer because most functions you would expect them to be continuously differentiable almost everywhere, including the absolute value functions. Okay, so here is the whole picture, and in fact, let me draw a diagram here to explain this. So the one in red here, if f is continuous, is the largest set. Okay, here, and I've given examples everywhere. X is continuous, e raised to x is continuous, absolute value of x is continuous. Even f dash x as absolute value of x, you can work that it's continuous. Okay? So large number of sets, a number of functions which are continuous. A subset of that is the second, which is differentiable almost everywhere. So look at how my set of functions starts shrinking. Just observe the red one had 1, 2, 3, 4, but differentiable almost everywhere. What does it have? Well, it has x, absolute value of x, e raised to x. Okay, I have kept all of them. Yeah. Okay, I haven't really included a function which is not differentiable almost everywhere. So fine, that's okay. I mean, you need to come up with some weird function. But Lipschitz continuous functions are equivalent to this class, which is differentiable almost everywhere. Right? As exactly you pointed out, mostly you would expect that if it's an countably infinite number of points also where it's not differentiable, it's fine. It's Lipschitz continuous. Lipschitz continuous is somewhat easy, right? So, but still Lipschitz continuity is not equal, right? So this is still a subset relation. There are functions which are continuous but not Lipschitz continuous. Okay, this first. So let's write down these takeaway. There exist functions which we will not discuss now. Okay, so Lipschitz continuity is a subset of continuous F, which means there exist Lipschitz continuous functions. Sorry, there exist continuous functions which are not Lipschitz continuous. Okay, that's the first one. The second is f is continuously differentiable. What does that mean? A subset of this is continuously differentiable, which means the part in green that the derivative exists and it is also continuous. So if you consider absolute value of x, is absolute value of x differentiable everywhere? Well, there's a problem. It's not differentiable at 0, right? So you can't even talk about it's continuously differentiable. But yes, um, that green, in the green list, you have dropped absolute value of x. F dash x itself, if it's the absolute value of x, as I wrote here, then we don't have a problem. But f dash x is it's already, I mean, if an f for which f dash x is absolute value of x, hypothetical x, f is already continuously differentiable because f dash x, which is absolute value of x, is continuous, not a problem. So the green part you can see has shrunk a bit. Now it turns out that f being continuously differentiable is like saying that the gradient of f is continuous. That's the green part. The gradient being continuous is like saying f is continuously differentiable. So that is a green set. Then we shrink further. F is differentiable almost everywhere. So the gradient of f is differentiable almost everywhere. Just like earlier we had said in blue, f is differentiable almost everywhere. In the light blue, we are just saying that gradient of f is differentiable almost everywhere. The list has shrunk further. E raised to x and x are the only ones from this original list which are differentiable almost everywhere, because f dash x as absolute value of x is not differentiable. E raised to x's and x's. And it turns out that this set is exactly the same as the set of smooth functions. Okay. So you get an idea that f being smooth and f, what is the connection between f being smooth and f being Lipschitz continuous? What's the relation? Earlier we had said continuity here and smoothness there. Sorry? The gradient is Lipschitz continuous, correct? So f is Lipschitz continuous, then f is smooth. So f is smooth is a kind of subset of f being Lipschitz continuous. Okay, by the way, I have more detailed proofs, etc. on slide notes. Huh? X cube. Earlier, not here. Yeah, x cube and x raised to 4 are not Lipschitz. Are not Lipschitz smooth. Yeah. Hmm. Well, what is the double derivative of e raised to x is c raised to x, right? Hmm. Yeah, sorry. Actually, e raised to x is smooth only within a bounded range. So I think I've taken that liberty within a particular range. Yeah. So I have not stated that here. X is of course, but e raised to x is under that condition. Thanks for pointing it out. E raised to x is a caveat here. All I was trying to say is, well, so I could drop e raised to x from here. So I think doesn't hurt. To be very correct, let me delete e raised to x from here. That's correct. I will e raised to x is all I'm trying to say is Lipschitz smoothness is much rarer. So you have made it even more rare. Yeah. Okay. Anything else? Okay. So this is the relationship. What I want to do is leave you with this very important homework problem, right? And yeah. Okay. One more point. One more point. Okay. If recall that a function is Lipschitz continuous if the norm of the subgradient is bounded. We have already done that. Lipschitz continuity was in terms of the norm of the subgradient, which I raised, right? Being bounded. So that subgradient connection is also brought up. Now there's also a relation with convexity. Over a closed and bounded subset, f is Lipschitz continuous, and that if f is Lipschitz continuous, then that is a superset of f being convex. So you are now seeing also a relationship with convexity, right? I mean, I've given some hint of how there's a tussle, but that was not an explicit relationship. Here we are saying a relationship that is, if f is Lipschitz continuous on a closed and bounded subset of Rn, then that is a superset of F being convex. So that means if F is convex, then then F is Lipschitz continuous over a closed and bounded subset of Rn. Okay, so this is an interesting relation. A little bit more on this. So if a function F is strongly convex, we know that F minus mu times mu by 2 times norm x square is convex. That's how we derive strong convexity, by adding mu by 2 times norm x square. Right? So we could construct a strongly convex function by adding a regularizer to increase its curvature. Question is, can we similarly construct a Lipschitz smooth function from a given function? I give you a function f, it's not Lipschitz smooth. How do I construct? Exactly this, right? I said if I had a function f which is convex, I'll make it strongly convex by adding a regularizer. Right? The adding regularizer is like putting the orange lower bound, saying, oh, I will increase your curvature beyond the orange curve. Now the question is, it's convex. Can I make it Lipschitz smooth by upper bounding its curvature? Saying, oh, I'll subtract something from you. Right? So if I take should it be subtracting L by 2 norm x square? So this is a homework, okay? Or is it, so this is slightly different. What I've written is, I'm not subtracting L by 2 from L by 2 norm x square from G, but I'm rather subtracting G itself from L by 2 norm x square. Okay, so think about this. Is there a relationship between this form or, L by 2 norm x square being subtracted from G? So that's a question. Is there a similar result for Lipschitz smooth function? And the answer is, of course, if G is convex, there's a transformation. But what is that transformation? Okay. That's one question. I'm going to leave you with for this, right? So you have to derive this. In fact, if a function f is Lipschitz, smooth, if there exists an L such that subtracting f from the quadratic expression L by 2 norm x square is convex. Okay, so it's not subtracting, it's not adding. Sorry, strong convexity was adding a quadratic expression. Lipschitz smoothness is not derived by subtracting a convex expression from f. Rather, it's saying that despite subtracting f from L by 2 norm x square, you still have convexity. A slightly different statement. Okay. So this is one thing for you guys to register. And in fact, there's an interesting duality connection. What I'll also leave you with is, I want you to look back at the different losses. Okay, I'm going to leave I'm going to leave these slides. You need to understand them. I really won't have time to go over it. I mean, I'll assume you will have gone over it next time. So logistic loss, is it Lipschitz smooth? The claim is yes, it's Lipschitz smooth. How do you show it Lipschitz smooth? So I have given the proofs here. Hinge loss, is it Lipschitz smooth? Well, it turns out to be no, but it's Lipschitz continuous. Okay. And then multi-class logistic regression is Lipschitz smooth, very much like logistic loss. Okay. So logistic loss and multi-class logistic regression are very interesting because they have Lipschitz smoothness and convexity. That is point number 2. Hinge loss is only Lipschitz continuous and convex. Lipschitz continuous and convex. No Lipschitz smoothness, no convexity, no strong convexity. Right? And then least squares. It is Lipschitz smooth and strongly convex, possibly the best of the lot, what we want. This one. SC plus LS. Right? And then what happens if you add L2 regularization? So you have to think a little bit about it and come prepared, right? Right? Lipschitz smooth and strongly convex. That's interesting. So if moment I add L2 regularization, I get strong convexity, but that's of course Lipschitz smooth. Only L2 regularization is Lipschitz smooth, but Lipschitz smoothness may not be preserved under addition. Okay, we didn't talk about calculus of Lipschitz smoothness. We will not, right? So you have to be a little careful. Is it that Lipschitz smoothness just I add a regularizer and it remains Lipschitz smooth. And finally, L1 regularization gives you only Lipschitz continuity, not even smoothness. Right. So you'll need to do a bit of reflection, and we'll conclude this part and move on to algorithms in the next class. Is it okay? So we meet on Thursday. I want to get a very good head start into algorithms and their convergence. And algorithms will just take a few, I mean, half an hour. The real part is the convergence, which will motivate more algorithms. And therefore, a good understanding of these properties will help. Yeah, we'll conclude here. Thanks.